in this video lecture we'll be solving this problem, cheapest flights within K-stops. We've already solved this problem with two approaches in my previous two videos, and I've attached the links to those videos in the description below, so make sure to check them out. So in this problem we're given n cities connected by some number of flights. We're also given an array of flights where each element in the flights array is a tuple representing three integers, where we have our starting city, an ending city, and the price to move from the starting city to the ending city. We're also given three integers src, dst, and k representing the source city, the destination city, and the maximum number of stops which are allowed to move from the source city to the destination city. And we have to find the cheapest price to move from the source city to the destination city such that we have at most k intermediate stop. If there is no such route, then we return -1. So in the input we will be given the flights array having n tuples, a source city, a destination city, and an integer k representing the maximum number of stops allowed to move from source city to the destination city. While in the output we have to return an integer representing the cheapest price to move from the source city to the destination city. So let's better understand the problem statement using an example. So here we have an exemplar test case where we have a network of 4 nodes numbered from 0 to 3, and 0 is our source node, city number 3 is my destination node, and the number of stops which are allowed are 1. So we are allowed to have at most one stop while we move from the source city to the destination city. Fine. So let's see how we can solve this problem. So here we have my source city which is city number 0, and one of the path to move from city 0 to city 3 would be move from city 0 to city 1, then from city 1 to city 3. Fine. While giving the price as 100 plus 600, that is 700. Fine. Another way to move from city number 0 to city number 3 would be just move from city 0 to city 1, then from city 1 to city 2, and finally from city 2 to city 3, giving me a total amount of 100 plus 100 plus 200, which is 400. Fine. So but we can see that along this path we have two intermediate cities, city number 1 and city number 2, which is not allowed because we are allowed to have at most one city while we move from the source vertex to the destination vertex. Hence this is out. So the only option that we have is the first path with the price as 700. Hence the answer for this test case is 700. So we move from source city 0 to destination city 3 with a price of 700 units. Fine. So let's see how we can solve this problem. Let's build the intuition to solve this problem. So here we have our sample test case or network. Fine. So we have 5 nodes here. The source node is node number 1, the destination node is node number 3, and we have at most 2 stops. That means we may have at most 2 stops while we move from the source city to the destination city. Fine. So in the previous 2 videos I have solved this problem using BFS and Bellman-Ford algorithm, while in this case I will be using Dijkstra algorithm to solve this problem because this is a single source shortest path problem. We have a source node and we want to find the distance till each node of this graph, or rather shortest distance till each node of this graph, which can be found using Dijkstra algorithm. Fine. So we know how Dijkstra algorithm work. In Dijkstra algorithm we greedily pick the node according to the cost. So we pick the node which has the least cost. So we start from the source node which is node number 1, then I push all its adjacent nodes into the priority queue. So we use a priority queue which sorts the given nodes according to their distances from the source node. So I have pushed node number 2 and node number 3 into the priority queue. They will be sorted according to their distances from this source city. So 2 will be at the top of the priority queue while node number 3 will be at the bottom of the priority queue because the distance till city 2 is lesser than the distance till city 3. Hence, and we know that the Dijkstra picks the node which has the lowest price or lowest cost. Fine. So I'm assuming that, so here at this point I'm assuming that you have a basic understanding of Dijkstra algorithm, how it works and its fundamental details If you do not have idea about Dijkstra algorithm, then I will ask you to read about Dijkstra algorithm. I will attach the resources in the description below. So make sure to check them out and read about Dijkstra algorithm to better understand the solution which I am going to explain here. So here I will simply be modifying my standard Dijkstra algorithm a little bit. So what I'm going to do, we know that we have a constraint here. So we cannot use a standard Dijkstra, which you simply start from the source node and keep exploring its adjacent nodes, keep picking up the nodes according to the distance greedily and explore all the nodes of the graph and finally return the shortest distance till the destination city. We have an upper bound in this problem. We can explore a path of maximum length of 4 nodes. So we can explore a path having a length of maximum 3 or having maximum number of nodes as 4, because only in such path I will have at most 2 stops. In any path which is longer than this path, which is longer than 4, which have nodes more than 4, is not a valid path, because that path would have stops more than 2. Fine. So we have to modify our Dijkstra algorithm a little bit here. So in the previous 2 videos where we used BFS and Bellman-Ford algorithm to solve this problem, I used a distance array. So what I did there, whenever I arrive at a node with a cost lesser than the cost which we already have in the distance array, then I performed a relaxation over that node and I update the distance array for that particular node. That was the strategy which I used in the previous, but in this case, rather than using the distance array, I will be using the stops. So what does this stops array represent? Stops I represents the minimum number of stops which I have explored to reach the city number I. Fine. So to reach city number 2, which is this, the minimum number of stops would be 0. To reach the city number 4, the minimum number of stops would be 1, because I can move from 1 to 2, then from 2 to 4. Similarly, to reach node number 3, the minimum number of stops would be 0, and so on. So that's what I am doing here. So this will simply help me to find the cheapest cost path with minimum number of intermediate stops. How? Let's see that. In the priority queue which I use in Dijkstra algorithm, along with the node, I will push its distance from the source city. So the first integer represents the distance from the source city. The second integer represents in my priority queue, I will be, along with the node, I will be pushing its distance. So first I will be using distance. So this dist represents the distance of the node from the source city, and I will also be using third integer, which is stop, or let's call it stop because we have stops array here. So we call it stop variable. So what does this represent? Or rather, let's call it steps. So what this pair represents, it simply says we have arrived at this node. Its distance from the source city is this, while the steps that we have taken to reach this node are these steps. Fine. What does this steps represents? So it represents the number of stops from the source city. Fine. So since I'm using a priority queue, it will sort these triplets according to the first variable, which is distance. So as in the standard Dijkstra algorithm, I will greedily pick these triplets according to their distances from the source. So initially I push this triplet for node number 1 or source, that would be 0, 1, and the steps would be 0. So this is my priority, while for the source city the stops array will have 0 stored here. Now I pop this node from the queue, from my priority queue. So I have node number 1 now. So I am exploring this city, which is the source city, and this is popped out. And what I am exploring, so here we will check for this triplet 0, 1, 0. First I will check in this stops array for the source city if I have reached this source city along some path which has fewer steps than the steps which we have here. But we can see there is no such case. The number of stops for city 1 in this stops array is also 0, as it is in this. Or I also check if the steps exceeds the limit. So what is the limit for the number of steps? We can take k plus 1 step, because we may have k intermediate nodes and one destination node. So including the destination node, we may have k plus 1 maximum steps, and k plus 1 is 3, and we can see that 0 is less than 3, so we haven't reached the limit. Fine. Hence I can explore the adjacent nodes of node number 1. So what are the adjacent nodes of node number 1? Which is node number 2 and node number 3. So I will push these triplets for these nodes into our priority queue as well. So what will be these triplets for node number 2? We can see that the distance will become 10, because that is the distance of node number 2 from the source city and its number, and the steps would become 1, because I take one step to reach this node. Fine. Similarly, for node number 3, I would have 50, then I would have 3, and the steps would be 1. Fine. And I push these pairs into my queue. So here I can see that these triplets are sorted according to the distance. So the triplet which I am going to pop out would be this top triplet, which is 10, 2, and 1. So I will pop 10, 2, and 1, because this is present at the top of the queue. So this is out of. So here I can check if the number of steps for this particular triplet. So this stops, and so I forgot to mention that this stops array is initialized with infinity. Why? Because I haven't arrived at any node yet initially. Fine. So here I have taken one step to reach the city number 2, and I compare this step with the steps which I already have in the stops array. So for city number 2, the steps which I already have are infinity. So 1 is better than infinity, so I store 1 here. Fine. So why? Because 1 hasn't crossed the limit of 3, and 1 is better than infinity. Hence I update the number of stops for node number. Fine. And then I explore its adjacent nodes, the adjacent nodes of node number 2, which are node number 4. At this point I have the number of steps to reach the node number 2. I also have the minimum cost to reach the node number 2, because that's what the Dijkstra promises. Dijkstra promises the cheapest price or minimum cost to reach each node. Fine. So whenever I pop a triplet, that triplet contains the minimum cost for that particular node to reach that node starting from the source city. That's what my Dijkstra algorithm guarantees. So the minimum cost to reach node number 2 is 10. So I have to check if node number 2 is the destination node or not. It is not the destination node, so I move to its adjacent nodes. So what are the adjacent nodes of node number 2? Node number 4 and node number 3. So I push the triplets for node 3. It would be, so for node number 3, if I arrive at node number 3 through the node number 2, the cost would become 10 plus the cost to move from 2 to 3, which is 30. So I forgot to mention it here. So it would give me 10 plus 30, which is 40. 43, and the steps would become, I have taken 2 steps to arrive at node number 3 through node number. Similarly, the triplet for node number 4 would be the cost, which is 10, which is the cost to arrive at node number 2, plus the cost to move from 2 to 4, which is 10. So 10 plus 10 is 24, and the steps would be, so I have taken 2 steps to arrive at node number. Then I push these triplets into my priority queue. Fine. So this is my queue that we have here. So this will be the status for my queue. We have these triplets sorted according to the distances from the source node. So I will pop the top triplet from this queue, which is this 24 and 2, corresponding to the node number. So first I will check if the stops has exceeded the limit or not, and answer is no. The limit is 3, while the stops here are 2. Then I will check if the number of stops which I have here in this triplet is better than the stops which I have in the stops array. And the answer is yes, because we have infinity for node number 4, because I take infinite steps to node number 4, because I haven't arrived at node number 4 through any path. This is the very first path. Hence I will update the node number 4 with this. Then, so this is popped out. Then I will check if this node, which is node number 4, is the destination node or not, because the distance here is the minimum distance for the corresponding node, because that's what the Dijkstra guarantees. And the answer is no. 20 is not the minimum distance to reach the node number 4. Hence I traverse its adjacent nodes, which are 3 and 5. So for 3, if I reach through node number 4, the cost would be 20 plus 15, which is 35, and this is node number 3, and the steps will be 3 now. Fine, 1 2. Similarly for node number 5, if I arrive here through node number 4, the cost would be 25. It is node number 5, and steps would become, I push these triplets into the priority. Fine. So this is my final priority queue after I push the node number 5 and node number 3, arriving through node number 4. So then I would pop this node out of the queue, which is node number 5. Corresponding to that node, we have triplet as 25. So here I can see that first I will check if I have exceeded the number of steps, and the answer is no. The steps are 3. Then I will check if the number of steps which I already have in the stops array is better than the steps which we have here in this triplet. So for node number 5, we have infinite steps, so 3 is better than infinite. So I will update this stops array with 3 for node number 5, and I will check if node number 5 is the destination node, and the answer is no, it is not the destination node. So I will move to its adjacent nodes. So before moving to its adjacent nodes, let's ask ourselves if it is optimal to traverse its adjacent nodes. I can see that I have already covered 3 stops to reach at node number 5 here, and to move to its adjacent nodes, I will have to cover 4 stops or 4 steps, and those nodes will simply be discarded because I have exceeded the limit of the number of steps, which is 3 here. Hence, it is not optimal move to push its adjacent nodes into the priority queue. So I simply pop this tuple out of the queue. Fine. Then I will pop the next tuple, which is 35, 3. So here I can check if the number of stops which are here, 3, are greater than the number of stops which we have here in this stops array. So I can see that for node number 3, the steps which we have in the stops array are infinite. So this 3 is better than infinite. I can update it, but I also checked if the node which I have here is the destination node, and the answer is yes, 3 is the destination node. Since this is the destination node, the distance which we have corresponding to that node will be the shortest distance, or it will be the minimum price or cheapest price, because that's what the Dijkstra guarantees. In the Dijkstra, whenever we pop a node, the distance corresponding to that node has to be the shortest distance. Fine. So 35 is the answer for this particular test. So I return my 35 right from here. So what I checked here, I checked if the stops do not exceed my limit, and if I have arrived at the destination. If these two conditions are satisfied, then I can return my distance right from here. Fine. And the answer for this test case is 30. Let's see the implementation of the idea which I explained here. So this is my find cheapest price function, which takes in the flights array of size n, source city, destination city, and the upper limit for the number of intermediate stops. I declare an adjacency list which will be used to store the graph. I prepare my directed graph. I declare a stops array of size n, all the n nodes. I initialize with it with a very large value. I declare a priority queue, and I initialize it with the source node. So I push source node, distance of the source node, and the number of steps to reach the source node. So this priority queue will simply sort these tuples according to the first variable. So here I'm running my Dijkstra algorithm. While the queue is not empty, I pop the top element of the priority queue. I segregate the 3 variables, namely the distance, the node, and the step. Here I'm checking if the steps which I have here for this particular node exceeds the step which I already have in my stops. If this is the case, or the number of steps exceeds the limit, then that means we already have a better answer. So here we already have a better answer, and here we do not need to explore its adjacent nodes. And in both of the cases, we simply continue to the next node. We do not have to process its adjacent nodes or to update the stops array. Otherwise, I update the stops array to the new steps which I have here, and here I have to check if the node which I have here is the destination node. If it is the case, then the distance corresponding to that node is the minimum distance to reach that node, because that's what the Dijkstra guarantees. Then I will explore its adjacent nodes, and I will push the corresponding tuple for those nodes. So for any neighbor node of the current node, the distance would be the distance for that parent node plus the price to move from node to the neighbor node, and I will push the neighbor node while the number of steps will increase by 1. Fine. If I have never arrived at this condition in this while running this algorithm, if this condition is never satisfied, that means I will never be able to reach my destination city. Hence, I will return -1 right after I end my while loop. Fine. So this is how the algorithm works, and it will compute the shortest distance or cheapest price to reach the destination city starting from the source city. Let's see the time and space complexity for this. So in this algorithm, I'm processing each edge at most k times, which is giving me this time complexity a multiplied by k. And for each edge, I'm using the priority queue. So I'm pushing all those e multiplied by k elements into the priority queue. And for each element, the priority queue takes logarithmic time. So this log factor, so to push and pop e into k elements, it will take log of e into k time complexity. While I'm using a stops array, that would consider a big of n time complexity. So I'm adding a linear time complexity here because of the stops array of length n which I am using. So the overall time complexity will become n plus e into k into log of e. Fine. While the space complexity for this implementation would be big of n plus e into k, because where n accounts for the stops array and e into k accounts for the priority queue I'm using, because in the priority queue I can have e into k elements. Fine. So let's see the code implementation for the idea explained here. So this is my solution class where we have a find cheapest price function which takes in the flights array, source city, destination city, and the maximum number of intermediate stops allowed. I declare an adjacency list to store my graph. Then I prepare my adjacency list using the directed edges from the flights. Then I declare the stops array of size n and initialize it with a very large value. Then I declare my priority queue, which will simply sort the tuples according to the first integer. Then I push my source vertex into this priority queue along with its distance and the number of steps to reach. Finally, I run my algorithm, Dijkstra algorithm, where I pop the top node from the queue. I segregate all the 3 factors. I check if the steps to reach this node exceeds the steps which we already have for the stops array, or the steps exceeds the limit which we are given for the problem. There is one of these cases, then we continue to the next node. Otherwise, we update the stops array and I check if the current node is the destination node. In that case, I will return the distance and then I will explore its adjacent nodes and I will push the corresponding tuples for the edges. Finally, if during this entire process I do not arrive at the destination node, in that case I will return -1 right from it. So this is the implementation in C++. Let's see the implementation in other languages. So this is the implementation in Java and this is the implementation in Python language. So that's all for this video. If you like the video, then hit the like button and make sure to subscribe to my YouTube channel and give your feedback in the comments below. I will see you in the next video. Till then, take care. Bye bye. And don't forget to the previous 2 videos for the same problem which I have explained here using BFS approach and using Bellman-Ford approach, because that would give a better insight for the approach which I explained here. Fine. So thank you so much.